First, let us establish the toolkit we will be using to work upon the task of squaring the circle. We begin with the standard 3, 4, 5 Pythagorean triple, shown with its 36-degree angle marked between the leg of length 4 and the hypotenuse of length 5. From the same point on the graph, we also see a 45-degree angle, labeled line, that extends to a height of 4 by the time the Pythagorean triple is at its peak height of 3, while the hypotenuse, extending at 36 degrees to a distance of 8 and a rise of 6, is a line segment measuring exactly 10. The 45-degree diagonal from one corner of an 8 by 8 square to the opposite measures an inequality of roughly 11 1/3. This demonstrates the effect of doubling, or multiplying all parts by the same sum, on any Pythagorean triple. In this case, we find that a triangle of side lengths 6 and 8 and a hypotenuse of length 10 is also a Pythagorean triple, because it is simply the 3, 4, 5 triangle multiplied by 2. Graphically, we can see this depicted as, literally, 2 copies of a 3, 4, 5 triangle inside the area of a larger 6, 8, 10 Pythagorean triple. The addition of a 3 by 4 rectangle of 12 unit squares completes the area of this larger doubled Pythagorean triple. While the area of the Pythagorean triple, whether the 3, 4, 5 or the 6, 8, 10, remains a measurement along, and in this graph below, the 36-degree diagonal line segment, the right equilateral triangle along, and again below, the 45-degree diagonal line segment, remains a larger area than that covered by the Pythagorean triple's expansion rate. We can also see part of the reason for the relativity between the 36 and 45-degree angles of expansion, contraction, is due to the arc radians of each square's width, measured horizontally, relative to its height, measured vertically, aligning along both the 36 and 45-degree angled line segments in the 3rd, 4th, 7th, and 10th iterations. As stated earlier, for any triangle with whole number sum side lengths, it will also have a whole number sum for its area. Thus, the area of the 3, 4, 5 Pythagorean triple is 7 unit squares in total area, and the area of the 6, 8, 10 Pythagorean triple is 24 such base 1 unit squares. Just so, for the 8 by 8 equilateral 45-degree triangle, the total area is made of 26 such unit squares. Within the geometric context, some of these unit squares inside the areas of these triangles are incomplete, though, once all added together, they necessarily sum whole number sums. Thus, this is the primary tool we will work with while squaring the circle. So we see in this depiction the, by now already familiar, 3, 4, 5 Pythagorean triple, nested as a 36-degree angle triangle inside a 45-degree angle triangle that, in turn, extends from the midpoint to the corner of three squares, each with the same center, but each with different areas. The central square is a 6 by 6 equals 36 area square. The outer square, an 8 by 8 equals 64 area square. And between them, in red ink, is the square of 7 by 7 equals 49. Now, given the formula for the area of a circle being A equals pi r squared, where A is area, r squared is radius squared, and pi is roughly 3.14, we find that the area of a circle, also shown in red, with a radius 4 and an overlapping centroid is equal to exactly 50.27, a relatively close approximation of the area of the square of that circle, the 7 by 7 equals 49 square. Stepping up to the next iteration of expansion, we see the same familiar 3, 4, 5 Pythagorean triple measuring the 36-degree angle below and within the equilateral 45-degree triangle. Here we can see the 3, 4, 5 triangle rests entirely inside of 1/4 of an 8 by 8 equals 64 square that is inscribed by a circle with radius 6, which in turn is circumscribed by a 12 by 12 equals 144 total area square. Between these and estimating the area of the radius 6 circle is the 10 by 10 equals 100 square. The area of this circle is exactly pi times 6 squared, or 113. So, what began as a margin of error or difference of 1.27 unit square areas at the iteration of a circle with radius equals 5, already by the time the radius has increased to 6, this difference or margin of error has increased concordantly to some 13. While 13 may be at least a whole number, it does represent a significant margin of difference. Here we see the sacred geometry depiction of the ancients' circle-squared graph. We find in its midst the 3, 4, 5 Pythagorean triple, with its area of 26 base 1 unit squares, within the square of 8 by 8 equals 64, and at the furthest depicted extent of this expansion, the 6, 8, 10 Pythagorean triple, with an area of 24 base 1 unit squares. Here we may see that the 7 by 7 equals 49 square approximates the circle of 50.27 between the squares of 6 by 6 equals 36 and 8 by 8 equal 64. That the 10 by 10 equals 100 square likewise approximates the circle of 113 between the 8 by 8 equals 64 and the 12 by 12 equals 144 squares, and that the 14 by 14 equals 196 square approximates the pi 8 squared equals 201.06 real area of the circle between the 13 by 13 equals 169 and 15 by 15 equals 256 squares. This final iteration yields an offset or margin of error of 5.06, indicating the margin of error is not a continuously expanding gap within the infinitely expanding sequence, but that this differential fluctuates in range instead. Further study of how and why this variable alternates from lesser to greater number sums may indicate deeper insights into this sacred geometric process in ever larger size scales. All method of thinking along these lines is called, rightly, squaring the circle.